You are now muted.
While we're waiting, I'll go ahead and list some stuff that I'm going to present today with regard to procedure. Give you a chance to begin reading through it a little bit. Okay, ladies and gentlemen, let's go ahead and join the meeting. I've lost somebody, so give me a few minutes to take attendance real quick. Okay. I think we got everybody recorded in. How many of you took the optional quiz?
I did.
Thank you.
I did.
That's
You are now
4. Okay, somebody want to say something? There's 5. Good, good. You realize that was 14% of your quiz grade, ladies and gentlemen. And the reason is we've got some trial communication going on to make sure that they have resolved the spam problem. I'll be talking about that a little bit later. But your transmission, hopefully, for the quiz was the way you would normally transmit it. I didn't want to tell you how to do it. But whatever you've been doing, you probably continue to do it. And then I'll check and see if it went to spam, because some of them have. Then, at the end of our conference today, I'm going to ask that you send a trial transmission. And at the end of conference, I want you to exit conference and then send an email by way of FSCJ's email. So just get into your email and send me an email. And in that email, I want you to write, don't type, write the following words. I want my 10 homework points, which is what that transmission is going to be worth. Now, I'll repeat it, and I'll also repeat it toward the end of the conference. There will be a trial transmission, but it's going to be worth your time. It's worth about 5 homework points, which means 10 divided by 2. Get out of Canvas. Hello? Oh, somebody else got a dog. Get out of Canvas. Get to your FSCJ email. Send me an email, but write it. Write, I want my 10 homework points. Make sure your name is on the paper. And put 8 somewhere near your name. That tells me what class you're in. Everybody kind of follow that, ladies and gentlemen? 10 homework points, which is worth about 5 points, because all of the homework points divided by 2 yields 130 points. So you're really working on 5 points towards your homework score. And then make sure you put your name. Now, I have 2 of you have last names that have the same last name as students in my evening class. So, but you have different first name initials. If you will then, if you just want to put your last name, but I do need a first name initial to distinguish you from the other class and to make sure we get you in the right class, in the right folder, would you put an 8 at the end of your name or something to indicate what class you're in? So that will get you to the right folder. You don't have to put the date, folks.
Did you want this written down or just email?
I want you to write it.
Okay.
I want to see what technique you're using when you write something or when you take a picture of something. If you want to take a picture of the page, they believe that the photographs that most of you are sending is not being transmitted clear enough. Some of you have even gotten emails from me saying, I can't read it, or it's blurred, or it's slanted, or it's in shadow. They're trying to figure out why the transmission is not as clear as it should be. So if you wanted to take a picture with your cell phone and transmit that, that would be a good test. But the best is, even if we can't do photographs, is to be able to write your homework or draw the diagrams and then just go ahead and transmit it through your FSCJ email. In writing the page, you may have to take a picture, or if you've developed a program or something, we'll see what happens.
And you
really have to,
at the end of class?
yes, at the end of class, please. It'll take too long for me to make sure everybody's done it before. And we do have other things to talk about. Namely, is what's on the screen right now, ladies and gentlemen. This is a procedure and a format for turning in work to be graded. If we're online, obviously we are. Part of this is the procedure that will probably be taught to you when you get into your field of study. And almost all of your fields of study in engineering and in computer science and in a biomedical field, you will be taking a course in ethics, which will tell you how to format procedures and about scientific communication. How many of you remember the first quiz? Anybody remember a communication problem involved? Oh, come on, almost everybody made a 3 on that quiz. The first quiz, we had some communication problems going on with a Mars lander and a Boeing 767, I believe.
It was the unit conversions. Why are they important? And it had to do with that like article that we read about, the Boeing and the space thing, the landing.
Oh yes, communication. Communication comes in more ways than just talking or writing. It's the procedure you use and the understanding that you have a common procedure. It also is in the way you format material. Ladies and gentlemen, it's fine if you start talking about equations, but in the scientific world, and particularly in computer science, symbols mean something. In fact, symbols can mean several words, so you save space. If you're not sure that they understand what your symbols mean, you may want to give the equations such as the summation of F equals A, subsistence, the system, times the summation of mass. That is Newton's second law expressed so that the sum of F could mean more than one force acting on the system. And you may want to put that in parentheses to the right of your equation. Usually that's customary. Some books, however, will describe the variables, and then they write the equation, and then they give it a number. And then they proceed to show how the equation is applied. In fact, your book uses that technique. In the laboratory, some of you are not looking at equations more than applying them. But if you go back to the information we have on laboratory, you realize that every problem in science requires 3 steps. Does anybody know what the first step is in problem solving? Now, there was a lady that answered that last question. Do I have a gentleman that wants to step forward? What is the first step? The first step in problem solving in the scientific world, and I mean
It looks like
biomedical.
Henry tried writing out what his answer was if you wanted a guy to answer.
Yeah, that's fine. You can read it if you want.
He wrote that write what equation you're using first.
Oh yes, write the equation down. I'm sorry, something was blocking your reply, Henry. And Clayton, it was about units, but more so communication. And the communication there was to get the right unit. So I even went back further in the theory there. It's got to be communication. Oh, absolutely. First step is to write the equation. Now, if you're using the equation to do homework, you don't have to explain all the symbols because we're into studying a chapter together. And fortunately, I have a degree in physics, and I can read your equation. If, however, you're communicating with someone that may not know what the symbols mean, and this is excluding homework, if you're writing or trying to help somebody as a tutor, you may want to write out what the variables are equal to and maybe give them an example. But we're beyond that. We're into reading equations and symbols. What's the second step in solving problems scientifically? Second step is probably the most obvious step.
You are now unmuted.
Write out the variables that you currently have.
Well, actually, a better way of saying that is to substitute for the symbols what the actual numeric values are. Now, that may mean that you've used an explicit equation or an implicit. The explicit is to isolate the unknown variable. I don't mind which version you use. I can follow it. And it might save a step instead of collecting to isolate the variable that you're trying to find or the unknown to the left side of the equation, since the world reads from left to right. Now, I know some cultures write from right to left, but in their scientific documentation, it is left to right, folks. Most of you are aware there's an international version of your textbook, and it goes from left to right. And I've seen that textbook, Survey, used in Nepal. When I was in Nepal for a month, and I visited the University of Kathmandu, guess what book they were using? Survey. In fact, I believe it was about the 6th edition. In fact, I asked, because their laboratory was so poor, where did they get the lab experience? And obviously, it wasn't virtual labs. What they had was a cooperative program with Georgia Tech, where their students went to Georgia Tech, usually 3 summers, between their freshman all the way through their junior and senior year, where they did laboratories that related to the content they were currently studying. So most of their engineering is agricultural-based, but some of it is also infrastructural, or maybe a traffic engineer of some kind, and that was quite interesting. So certainly your textbook, if it's being used internationally, is going to read from left to right and has the same format that in fact, every page in that book had the same page number as our book. Okay, folks. Excuse me. Obviously, please place your, would somebody like to read the first dot?
Place your name and the chapter at the top of each page, including the date on the first page.
Thank you. I needed a drink. Excuse me again. I don't know what the problem is here. I know there's a number on microphone, so I try to verbalize. Separate your chapters. Now, if you can't, would somebody like number 2? Thank you again. Now, there may be, in some of the laboratory material or the resource material, lab questions or problems. In fact, this is about the only time you would encounter questions that were not associated necessarily with a problem, like part D of a problem. They are to be submitted on a separate sheet of paper and not attached to the lab. Although we're only doing an analysis of labs, we don't want to start putting questions in it, because in a scientific paper, you don't put questions at the end of your scientific paper, unless it's a question like further experimentation should be done, and we believe it should be done in the following way. If anyone has any questions, please refer to blah, 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 blah. Okay. Ladies and gentlemen, I have, as you probably know, I grade every one of your homework problems. And if you have a question about your homework grade, I recommend that you ask for a phone conference, and I'll be glad to tell you what's happening. But I kind of told you a couple weeks back that you're forgetting to put units. You're forgetting what order to problem solving that you're doing. And incidentally, we can go back to those steps in problem solving, a minimum of which would be 3. So the third step is to give your answer with proper units. You've been giving me answers with no units. You've been putting numbers in the the equation without units. Sometimes you have numbers with variables still in it, which is fine if you want to go to about a 4th or 5th step. And ladies and gentlemen, some of you have the wrong answer. Now, you have access to all the right answers, either at the end of a textbook, or if you look under general information, I have answers to all of the even number problems that I've assigned, plus a lot more that I have assigned in the past, or I have worked for myself to make sure it's right. So some of you, and I had one student ask me if there's any more problems they could work in order to get ready for the test, and the easy answer to that is just work all problems, all parts of a problem that may have been assigned only the first part, or work problems in the section where they may be having a little more difficulty, and pick problems that have an answer, either one on my answer sheets that I gave you, or answers in the back of the book. Okay. Some of you have very crowded homework, very difficult to grade. So if you could leave at least one line, maybe 2 spaces between problems. I don't mean between lines in a problem, I mean problems. Some problems may take the whole page. Some problems may take 4 lines and then skip 1 or 2 and go to the second problem you're working. Use single columns. I grade from top down, folks. If you want to use the right-hand side, since we read left to right universally in engineering and science, people would normally go to the right. So put A to the left, B to the right, C under A. You see how you're reading your homework like you're reading almost 2 lines or 3 of a book. Please use 8.5 by 11 lined or unlined paper, because when I pull up your homework and I go to enlarge the screen, I can't diminish, but I can enlarge your work if I'm having trouble reading it. Now, ladies and gentlemen, I'm nearsighted. I may be old, but my nearsightedness is improving, which is usually what happens when you're old. And sometimes I can actually grade homework without my glasses. So it's not my eyesight that's the problem, ladies and gentlemen. It's actually how it comes through or is transmitted. And I'm going to suggest that you use black pen, or a dark blue is working very well. What happens if you make a mistake? Just draw a line through it. I promise not to look at any work you have drawn a line through. That's easier to do than white out and all that. Just draw a line through it. In fact, scientific rough drafts usually will not erase anything in case what they drew a line through may indeed be something they want to use. It's only after you have your final draft will you probably not have any of those crossouts. So again, good scientific paper writing. And incidentally, some of you in engineering will be taking a course in scientific writing, ladies and gentlemen. Not only a course in ethics, but a course in scientific writing, particularly if you get your degree here in the state of Florida. It's easier to enlarge a page that's 8.5 by 11. I think you realize that. Your work must be large enough to read and should be organized to follow steps in your method without wandering all over the page. Do not cram work in very small spaces. If you find that you want to go back and add something to a problem, what you should say is on page 2, at the top of the page is the continuation of this problem, and then move on to the other problem, just to give me guidance as to where you can find the work. Obviously, your handwriting must be legible. And I'm going to kind of back out of this a little bit. Paper should have straight edges, no hanging chads from spiral notebooks. Please don't tear things out. You're entering a profession, ladies and gentlemen, and your work should look like it. Let's start practicing that now. I'll give you a story about, obviously being a woman, I do go to the beauty parlor and have my hair done on occasion, or at least get a haircut, which I haven't had since February. My hairdresser will take you on a one-to-one basis, but I don't want to get out yet. Make sure that when you're sending something online that the paper is flat, particularly if you're taking a photo for transmission. Some of you, I see your hands holding it down. Thank you. I appreciate that because it ends up being blurred. And if you don't write large enough, so the blur is obviously Z's instead of 2's or S's or something. The spiral notebook is, well, very unprofessional. Okay. Use numeric order when doing homework. In other words, number 2, then 11, then 34, etc. If a problem is skipped, then where the number should have been, make a note to direct me to the new location, which may be after problem 34, maybe on the last page of transmission, but be careful. Some of you do not have the last problem on the last page, so be careful. If it is out of order, and by the time I finish grading the problem, then I go to the next problem, this problem, which is out of order, may not get graded as of order it is out of. Well, that sounds like Yoda there. Pardon me with that. Work should be neat in dark pencil, and some of you do use pencil that is dark. I don't have a problem with that as long as I can read it. Or use black ink, and I had mentioned that some of you use blue, and it is coming out okay. When using yes or no for answers, use at least one sentence to clarify why it's yes or why it's no. That sentence should be complete, proper spelling, and proper punctuation. Again, ladies and gentlemen, we are starting out on your professional studies, and you will find very soon when you go through professional writing that even some of your drafts that your company will expect you to maybe take pictures of and put in a storage of emails for reference, they would expect that to be true. So just, explain why you said no to something. It can be short. In fact, a lot of the answers to questions are also more than one sentence in the answer keys. And so you may say, okay, I'll rephrase that. I don't consider that plagiarism. You're just using some of their words. Okay. If you do not have time to complete the entire assignment when it is due, of course, do your best. I prefer some work well done to all work messy and difficult to grade because you're trying to do it all. There is enough homework points. That's about 280 plus. And I take your homework grade and I divide it by 2 to get the 130 points. And we're going to be earning 5 homework points, and all you have to do is do some kind of transmission and some kind of writing. There will be opportunities to get other extra homework points. There is no need to try to be perfect in this course. I think you'll find in your profession that if you expect yourself to be perfect, you're going to burn out very rapidly. In fact, your supervisor or the director of whatever project that you've been given will probably ask you to come into their office, and they'll probably tell you that you're burning the candle at both ends. You need to slow down. Always check your answer with the given answers. Now, the labs with the questions and problems are exempt because I don't give the answers out to those because it's something that you glean from your action lab. If you don't, then later I will give you the answer, and that's where you need to concentrate on laboratory cause effect. As answers to even assigned problems are given, and answers to the odd assigned problems are at the back of your text. If you fail to check your answer, I'm not going to count any points at all, and some of your homework counted as much as 4, 5, 8, or 9 points. You don't want to lose points just because you failed to look at the answer in the back of the book and tried to go back and rework it. Drawing lines through your present work, and if it's out of order, say you'll find this at the end of problem, whatever the last problem was. Okay. I don't have a problem with this. Most of you are writing on one side of the paper only, which is what you need to do because sometimes transmission, we found last semester, if you wrote on the back, it bled through the actual transmission. And some of you probably knew that. I appreciate that. Is there any question about how you should be transmitting homework, quizzes, any other material to me? If you do, if you'll send me an email, and it may be something that we want to share with everyone. Most of you are following these guidelines with the possible exception of putting your name on every sheet of paper. In the other class, I currently have a lab with no name on it. So I've got to go back through all the emails and try to find who it was. Well, okay. The other concepts I would like to go over were mentioned in the material that described the conference for today. The discussion at the beginning of the class today was going to be turning in work to avoid work going to scam or clutter. Okay, ladies and gentlemen, here's what the tech team and maybe to some degree Canvas, you're going to be practicing this at the end of the conference. If you want to send anything, even the quizzes, get out of Canvas and send the email to my fscj.edu. And of course that's lowercase c dot, my last name, Dewberry, Dewberry, at fscj.edu. I don't know why, but sometimes when some of you even submit your quiz grade, your name and then in parentheses is the Canvas identification of this course. And when that happens, FSCJ's email considers it spam from what they can determine, and they send it to clutter. What we need to do then is get out of Canvas so it will not identify. The last spam I went through had 9 of you in it, folks. That's more than half the class. So it's overworking itself. It's doing something it shouldn't do. But we're going to try to solve it if we just stay out of Canvas, close it, go to your FSCJ email, and send what you have to send. And we're going to try that after we leave conference. And it's going to be worth 10 points, which is equivalent to 5 points out of 130. Again, a name on all pages turned in for grading. You could use only your last name is okay. If you include an 8 for this course, Actually, two of you really need to give me your first initial as well, because I have the same last name in my night class. Please label in your transmission whether or not it's going to be a chapter, and then give me the chapter, like chapter 5. Lab title or lab number. Lab number 1 is fine. Number 2, but you may want to put a title with it. That's fine. A quiz. This quiz was number 01, because it's really kind of zeroous, but it was interesting to ask those questions. And if for some reason a test page is not labeled, you might want to put, let's say, T2 on every page of the next test, as well as you notice there is a place for your name, and again, last name. I'll know by the test that we're in Physics 1 with calculus. When sending me a text or a voice message to my phone, give your name, and if you'll just say type 8 or something. Although if you give me both your first and last name, I will probably recognize that you are in Physics 1 with calculus, but it's nice to say 8 maybe, or 48. I would recommend that anytime you send me anything, that you CC yourself the email as well. This will help try to validate readability of content as you see it. And ladies and gentlemen, when I am, and I've tried this in Canvas, I've tried this with this at FSCJ. I've tried it on my computer's email. I've tried it with my family and my education. I find that if the address is not going to go through for some odd reason, maybe you have too many files, and FSCJ is bad about this, I find that you can transmit about, depending on how massive it is, about 4, maybe 5 pages. You get past about 6 and it starts dropping. You think it transmits the whole thing. To be safe, I would recommend that the next test we have, you're going to be transmitting the test pages to me with your work. And there's a reason for that. I had 2 students to send me the same work for partial credit. So when we put your name on it, I'll know whose it is. And if that happens again, ladies and gentlemen, 2 people are going to get a 0. I have discovered who had the original work, so I think it got resolved. That is cheating, folks. That is using someone else's work. Does anybody remember how the honor code was worded? And I had it modified for my course, acceptable through the student services. Does anybody remember how the honor code that I asked you to initial or sign or type in recognition, what did it say? Uh-oh. Actually, ladies and gentlemen, about half of you did not find the answer sheet that had the honor code on it. You must have gone to files, because I thought I had removed it from the home page. That will not happen again.
When I went to print it, that was the only thing that didn't print out with it, was that sheet. Like, I was able to see it when I pulled it up, and then I tried printing it 3 times, and I wasn't able to print that second, like that honor code that's at the bottom of the page.
You know something? I'm having trouble feeding and getting back a document similar to the document for the honor code answer sheet the last 2 days. So I believe you when you say that. I don't know what's going on with Canvas. But you see this page that I've got right here you're reading? I could not load it to the home page or the general, well, there's another file, any place. It wouldn't accept it. And one that I had sent, it's not letting me print it out. I don't know why. I am nowhere near the limits for data that should be in the course before it goes to a cloud somewhere where you can pull it out. I don't know what their problem is again, but I'm a little tired of trying to solve their problems. That was meant to be a little joke, folks. I didn't get any laughter. I hope those of you on microphone kind of chuckled a little bit then. Or
You are now muted.
on not microphone, ear things, what you call them. I would suggest that once you CC yourself that you wait just a few minutes, because I find that failure to transmit usually comes on within a minute. So if you're transmitting at that midnight deadline for homework, if you want to go to bed at midnight, try transmitting it at 1:15. I'm almost certain it will tell you that it didn't transmit. And then if you CC'd yourself, you're not getting it. Would everybody agree? That's 2 ways to find out you didn't get something. Do I have a yes on that somewhere?
You are now unmuted.
Yes, ma'am.
You are now
Oh,
muted.
thank you, Ashley and John. I appreciate that. I'm going to try to type out these suggestions that I put for the topic of the conference today, as well as the page that you're currently looking at. If anybody can think of anything else I should include on either of these pages, since this page you're looking at has not been received by Canvas yet, it is easy to modify. Please let me know, because a lot of this information we really generated last semester when we finished it on Canvas in the Physics 2 class that I was teaching at the time. It works pretty good, if I can just get it to you. With that in mind, I'm going to get out of conference, but if you'll stay on conference so I can hear your voice, I won't be able to see what you write. This is going to be a little like what we do with the labs, where I'm on conference and connected to you, so if you have a question or if you're talking to one another, I can hear you. And I do appreciate you helping one another, ladies and gentlemen. But when we do have labs, let me remind you that usually you have a quiz and we have a brief discussion, maybe some questions about laboratory, and then you are dismissed during the conference to do the labs, which means if you're not doing the labs and you're doing them over the weekend, when you send me an email about a problem you're having with the labs, ladies and gentlemen, if I'm not near a computer or if I can't answer it by the way I worked your lab, I've worked through every one of those labs, and I tried to pick labs that were similar to what we would have done in the classroom, rudimentary as it is. Yours is not as elaborate, certainly not hands-on. I really am prone not to go out of my way to answer questions about a lab you're doing on a Saturday afternoon, because you had release time to work on that lab. In fact, as I believe one of your labs was like 2.5 hours of release time, and some of you, you need to, don't send me an email on Monday afternoon saying, how many trials were we supposed to be doing, which you should have done that lab 2 weeks ago. You see the problem there, ladies and gentlemen?
You are now
Well,
unmuted.
I know.
You are now muted.
Ashley and John ought to give you points every time I see your name up here. But those that have earphones won't necessarily have an opportunity. I'm getting ready now to leave the visual part, so I won't be able to see your writing. And I'm going to go straight into a lesson on Chapter 13, the unlucky 13, unfortunately. I am technically out of Canvas, but I can hear you. I can't see anything that you're writing. Now, in order to know what I see, I'm going to ask you to go out of conference, don't exit, and go to the lesson outline, because that's what I just did. I went to a lesson outline. You still see a white screen, but I am on the text, chapter 13. It's the only chapter 13 in lesson outline, lessons PowerPoint. So take a few minutes to pull that up on your screen with Canvas in the background. Take a few minutes. And if you're having trouble, sound out, folks, because I won't be able to see your writing.
You are now unmuted.
Yes, it should say text
You are
by it
unmuted.
because I do not have a separate PowerPoint for Chapter 13. It is treated as if it were a general physics lesson, not a physics with calculus. So I just pulled down one that would be similar to the Survey book that has no calculus, because the one from your book is an overkill, ladies and gentlemen, according to the state mandated guideline for the content we should be studying. How about if I give you about 5 minutes to find, it says storyline, chapter 13, universal gravitation, and it looks like it has a spiral galaxy photograph here. That's pretty good. Resolution's pretty good, too. Anybody have any questions while we're waiting for everybody to find chapter 13? No questions?
No, ma'am.
Hey, I love this class. I just wish our homework looked a little bit better.
Ma'am, would I be able to have a conference with you at around like 9 o'clock tonight?
Yes. Can we make it a little later because of the content of the, yeah. How about 9:15?
That's fine. Whatever time works with you, ma'am.
Okay. What you need to do is call me. And if my caller ID is not going to identify you, I won't answer. Being an older person, that's the advice they give us. What you need to do is hang up and then call me back, because I would pick up on the fact that it's the same phone number, and then I'll know it's around 9:15, so I'll know that it's probably a student. Okay?
Yes, ma'am.
Okay, and then we can make contact. It's not that I refuse to answer. I just have to be careful. I have to look at the number, and once you're as old as I am, you'll find out that people think we got a lot of money, and they really tried to scam us.
Yes, ma'am.
Oh, yeah, and I'm not that naive, and the ladies that I associate with are not. Well, one of them got caught in something, but she didn't have enough money or anything, so she didn't have anything to scam. Please don't repeat that. I didn't mention any names. Okay. So, okay. All right, and make sure you identify yourself once you call, please. All right, got that. Good deal. Right. Oops. Here. Okay, I'm going to wait about another 3 minutes, see if I've got everybody. In fact, let me just go back to the conference for a minute and see if I still have everybody. Oh, I have more than I started with. Those of you that late, folks, you've missed out a lot of communication and procedure. As soon as the page that you see is allowed and canvas, I will put it under general information, and the title will be procedure and format for turning in work to be graded or turn in work online. I forgot what the title is, but and thank you for rejoining us, because with some of the difficulty we're having with Sam, I'm checking to make sure that everybody's name is present so you hear the technique, folks. I'm only missing one person. Give me a few minutes. I've got to take attendance again. Ignis. All right. I'm going to go back to the presentation. I'm going to go ahead and start. Obviously, there is very few homework problems from Chapter 13, because the only thing I'm really after here is, all right, I'm going to go ahead and enlarge the screen. I don't know if you would like to, but basically we'll be going over Newton's universal gravitation, which applies to the Earth only, or we're going to confine it to the Earth only. The discussion will be limited to the concept of the Earth's gravitational field and comparing it to the other planets. But that's all. There's no Kepler. That is not in the course description as mandated by the state of Florida. I'm sure all of you, with your experience in general physics, is aware of Newton's law for universal gravitation. Actually, this law was first presented as a gravitational force being proportional to the mass of the Earth and a mass that was, say, on the rim or standing on the surface of the Earth with respect to center of mass to center of mass. And its restriction or limitation is that the R, which is in the denominator, notice it is a square, R squared, square law, representing the distance between the center of the Earth and the center of whatever object was present on the Earth. And we know then that the restriction on R here is it's got to be equal to or greater than the radius of the Earth. The gravitational force inside of the Earth is an interesting study. It is more like an inverse cubic function. It's hyperbolic. Interesting study, but that's beyond most engineers' studies. And notice that capital G here is expressed to 4 significant figures, and your text uses only 3, but I think they want you to see why they rounded off to 7. 6.67 times 10 to the minus 11 Newton, meter squared divided by kilogram squared, And I would like to get rid of the dot that is between Newton and meter squared. Dot will mean something different to us if we get to it in the lesson this evening or afternoon. That proportionality was something that a man by the name of Cavendish did some experimentation based on a torquing effect, which we haven't even studied yet, unless you've had some general physics and you know that torque has something to do with rotation or turning, and was credited with one of the first measurements of this proportionality constant. And sometimes a lot of numbers like this are not proportionality constants. They fit the equations so the units work. Cavendish had an apparatus, something like you see in the next frame that we're at, or hopefully. The dashed line represents the original position, and of course it's been twisted out of alignment. In other words, these masses are trying to line up with one another because the initial line is out of line. By any chance, and I know that you're all very young, ladies and gentlemen, so you may not be familiar with Skylab, but that was something that was, I guess, a forerunner of the International Space Station, where they had something about as big as, I don't know, a medium-sized trailer, I guess, operating with solar panels. But astronauts would go up there and they would have packages along the walls there that contained certain type of experimentation. And one of the experiments was to release 2 spheres that were stainless steel into the atmosphere of free fall. Of course, it was confined to the box that contained the experiment. And astronauts could look through a window to see if indeed these masses in an orientation where they appear to have no weight whatsoever, so they're not falling. They're traveling about the Earth, just as the Skylab and all the astronauts were. And they began to observe and record how the 2 masses, and I've forgotten what their mass was, I think it was 300 grams, I'm not sure. Over time, these 2 masses begin to approach one another along their connecting lines. Well, they did some measurements, and they found that that was a unique way of verifying Newton's gravitational equation. Does anyone remember Skylab or know about Skylab? Hello? Do you hear me?
No, I don't.
You are now unmuted.
I can hear you, but I don't know anything about it.
All right, so 2 of you said that you can hear me.
Oh, we can all hear you. We just
Yeah, I can hear you.
Skylab is.
Yeah, I don't know
Okay.
much about Skynet.
Oh, okay. All right. Some of them haven't found it yet? Okay, let me wait a little bit longer, because this is only one concept in this chapter, and it is extremely important. This law is why we stay attached to the surface of the Earth and don't fly off or try to dig our way through the surface because of centripetal force. And I hope that almost everyone in our class knows about universal gravitation. After all, this lesson really is a general physics discussion. Very little calculus at this level. Let me backtrack maybe to, let's do it. Where's my clock? 1. I'll give them a few more minutes. In fact, if somebody wants to type, and everyone should type, yes, they found it, or just the word yes. If somebody would type that out, Ms. D asked if you will type yes if you have found the lesson.
I think we have the lesson. I just don't think we know what you were talking about in regards to that first mission or whatever.
Oh, the Skylab, yeah. In fact, in textbooks after that first was observed, it was included, but it's gotten to where that most of our young people would not relate to it anyway. But it's interesting to go back and look at that experiment. Now, it didn't last 24 hours because Skylab had to orientate itself in space, and since these masses were suspended, they got too close to one end of the box where the experiment was in, and as soon as it had impact, of course, it started like a pinball going all over the box, so it interfered with the experiment. But it was quite interesting to verify universal gravitation in an orbit that was of Skylab, which was at its, anywhere from 125 to 150 miles above the Earth, and that's not very much. That's less than half the distance from here to Tallahassee. That's eventually why Skylab fell out and ended up in the Pacific or something like that. Yeah, it was the Pacific. Okay. The equation, pardon?
When was that?
I'm trying to think back. Can I say a long time ago? I think it was in 60s. It's in the 70s, and it fell in the 80s, and that's probably before some of you were born. But I thought I would relate it if some of you wanted to research Skylab. In fact, that was one of the simpler, more significant experiments. So I would think they would mention it, or if you Google it, I would think that the experiments they did, which is extensive, might be one that they mentioned. Okay, here's another. This is kind of an example of those two steel balls that were there in free fall. And notice that the force is an action-reaction pair. It takes two masses to have an action-reaction pair that would obey Newton's third law. In fact, that's one reason why I formulated this quiz today, which was not really scheduled, is I wanted to, my quizzes usually relate to the last lesson as it would be applied to the present. I don't always hit that idea, but it's sort of, the quiz is designed to focus your thinking on the concept. So that if I use it in today's lesson, you go, oh, yeah, got it. There you go. And notice that when you go from just an equation in magnitude to one in vectors, the vector to the left is boldface. Now, I use that technique also in my quizzes because I can't draw an arrow over it. And notice that this particular lesson has an R over it, which implies that you've got to look for a normal radial position, just as gravity works through your center of mass to the center of the Earth, and it is inward, which means it's negative. Down is negative. And then they added a vector with a little, looks like a boomerang at the top, caveat, and they say sub R, sub 1, 2 for R. Now, by convention, the force on mass 1 comes from mass 2. That's why the subscript is F sub 2, where it comes from and where it acts. This is part of the symbolism, again, of science. In fact, it becomes fairly important in medicine to know which paramecium you're dealing with or which mass or glob you're dealing with. However, the magnitude of these two forces would be the same. One is just in the opposite direction from the other. And then they give the equation as if we're dealing with the mass of the Earth. And as I mentioned, the emphasis will be on mass of the Earth planetary. There are some restrictions on the use of universal gravitation. I have given one, and that is that this radius here has got to be equal to or greater than the radius of the Earth. Another limitation is one of those masses, in the case of this frame 4, notice M sub 1 is considered the mass of the Earth, and it's capital out. Capital M implies that you're dealing with an astronomically large mass. Universal gravitation, this form of the equation only works when one of the masses is astronomically large and is a sphere. So we have three limitations on this equation. Now, I know in general physics you were taught this is the universal gravitation equation. And those courses usually don't talk about limitations. But we've got to talk about limitations. The real world, and science in particular, and medicine very much so, has its limitations. So we have three restrictions so far. All right, with that in mind, they have sort of a quick quiz here. Ladies and gentlemen, if you really wanted time to do this, I would recommend you do it at some later time because we've got to move on. I know that on your next test, I will probably, well, I've made it out. If you have any problems from, or any questions, or any test questions from Chapter 13, there'll be one of them. So the time frame is important here. If you go to the next frame, it'll give you the answer anyway. Whoops, wrong. And notice, this is the inverse square law. As you review, maybe this chapter is going to give you the answer anyway. Then notice that this is similar to an example in your text where you're dealing with three planets. Well, notice that they're using a mass here far less than an infinitely large mass. But they do use spheres. They just happen to be, what, billiard balls? To kind of prove the point. And also notice, for convenience, anybody want to tell me what size is the size of these triangles, and maybe why they have the sizes that they do, or the distances they do? What's the value for A, B, and C? Little a, little b, and little c in frame numbers.
Step away for a moment. What slide are we on? What slide number?
Number 7.
Yes, ma'am.
Yeah. It's just like the books. Ladies and gentlemen, try not to be away from our conferences. And ladies and gentlemen, I know I just talk on and on and on, and I never take a break. Somebody needs to remind me, Mr. Berry, can we take a break?
Could you repeat the three limitations?
Pardon?
Could you repeat the three limitations you mentioned?
I don't know who's talking, but I'm getting feedback from either my phone or yours. I think you said 3 limitations. Okay,
yeah, what was that?
That's louder, a little bit better. Loudness apparently sends it through without resonating wherever you're at. Okay. The first was the fact that the R value has to be equal to or greater than the radius of the astronomically large mass. So that's really 2 in 1. You got the radius has to be equal to or greater than the radius of the planet. One of the masses must be astronomically large. And the third is it must be spherical. Now, ladies and gentlemen, if you know anything about the Earth, you know that it's not perfectly spherical. In fact, the lower portion, the southern hemisphere, bulges, so the Earth is a little pear-shaped. But we're forgiving that in our study. If you go into physical physics or geological physics, that will be a whole course you take into how to manage that, whether or not you're in some of the Southern Sea, the South Pacific or South Atlantic, or whether you're on a landmass. But that's, again, beyond our study. Notice that it says, calculate the gravitational force vector on the cue ball designated M1. Now, usually, when you are interested in summing vectors, you want to place your reference mass at the Cartesian coordinate origin. Please note that that's exactly what they did. However, you could actually put it anywhere. However, on a test, you better know where it's been put. If it's not stated, then the reference mass is always given Cartesian coordinate or Cartesian coordinates of 0, 0, 0. That's 3-dimension, and we stay away from 3-dimension in chapter. Okay. Well, they've done the calculation with the two masses. Notice they've implied there's an I and a J direction because the other masses are lined up along the Cartesian coordinates. And then they add the forces. Please note that the sign of the IS and JS components are both positive, which should tell you what quadrant it's in, ladies and gentlemen. What quadrant is it in? Yes, thank you. Some of you are finding angles, and you have a arctan of a numerator, which is always positive, and a denominator, which is always positive, which is not true. It is only that way if both the I and J are in the first quadrant. And suddenly you get the right answer. The second quadrant, I think you had homework in the third quadrant, one in the fourth quadrant. I take points off if you have the arctan of, say, I don't know, 5 divided by 4, and you end up with something in another quadrant. Your notation is not being honest. You need to, when you do the arctan, the rise over the run, if the JS component's negative, that numerator better have a minus sign in it. Again, that's communication. It's telling people what you got, according to your diagram, of course. Here's where you're finding the magnitude and the angle, and notice that they have not only the equation, the substitution of data, and then the answer. Tan, notice they have the expression, and they know to get the angle, you do the arctan, or the tan to the minus 1, and the values. So you can at least see 3 steps there. Actually, some of you did this when we were doing vectors in Chapter 3 in your homework. And when you were in the first quadrant, it was perfect. Then we started moving out of the quadrants, and that's when you had a trouble with the angle being the arctan. Free fall acceleration and the gravitational force. And notice that as a way of measuring the gravitational field strength on a mass M, not capital M sub E, we want to identify the force of the Earth on us, which is our weight, and a lot of you have already indicated in Chapter 5, you know that equation is mg. I believe that was in Section 3 of Chapter 5. But then when you equate it to universal gravitation, you find that that small mass, infinitesimally small mass, as my mass is compared to the Earth, cancels out of the equation. And we find that that first limitation we had, where the radius of the Earth is the smallest radius in the denominator, we could add an altitude, h, which would be over and beyond the radius of the Earth, and get an equation for the acceleration due to gravity, if we knew the mass of the planet and whether or not we are at the surface or above. And I am particularly interested in Table 13.1 as resource material. And notice that it tells us that at an altitude of sea level, the acceleration due to gravity is 9.80. This is the value given to in every book, and I've already mentioned they used it in Nepal, and Nepal is higher in altitude than Colorado Springs Air Force Academy, and they use a diminished value because they are a mile high. They use 9.79 because it's less. It's divided by a larger radii, G M sub E. The radius at sea level here in Florida is slightly higher. I think 3 of the state universities have actually done this experiment and found it's about 9.8078. So you could almost round off your acceleration due to gravity when you do laboratory work in the state of Florida as 9.81 to 3 significant figures. Depends on whether or not you're downstate. It might not round off to that. But you get to Tallahassee, and Tallahassee is one of the high points in the state. It will get closer to the 9.80. Anybody going to go to Florida State? Don't answer that. I'm a graduate of Florida. Thank you. Okay. Here we go. Here's another one of the quick quizzes, and if you wanted to go back and study it, you would find that they will give you the answer. This is where it's some kind of baseball and it's in orbit, and I just mentioned it would be slightly less than the 9.8 because you're dividing by a larger R value. And here is using the known radius of the Earth and the acceleration due to gravity, find the average density of the Earth. Well, anybody going to go into geological physics will be quite aware of this. And it talks about the inner core must be more dense than the outer. Interesting discussion, not really interested in it, so I'm going to move right on. And then particles in a field, interesting enough, I'm not really interested in this material. So if you wanted to identify the frames that are important to us, it will be from 1 to 15. However, and I don't believe anybody has declared that they're going to be a physics major. If you plan to be a physics major, I would recommend that you do a little bit of this analysis or at least read through it. I'll go through a couple of frames. Notice that this tells you the vector position of gravitational force. It is radially inward in a three-dimensional sense, and they have only got a slice of that 3 dimensions. Talk a little bit about particles in the field will move toward the Earth, and notice move perpendicular to the Earth from rest. International Space Station, interesting talk there, the weight in space, and they tell you the weight. This weight is less than its weight. And the reason, please note, is because the R value is higher. It has a weight of 4.1 times 10 to the 6 newtons, and in orbit it has an apparent weight of 3.7 times 10 to the 6 newtons. It appears to have lost some weight. Remember that, because it is in Chapter 6 lesson as well. Move through a little bit. Kepler's law, no. Interested in astronomy. I have a star plotter on my phone at night. It will locate me and it will tell me where all the planets are. We are all interested in outer space, but no. This is already 5 frames beyond where we want to be. So we'll move on then to Chapter 6. And let me do this. I'm going to get back to shrinking it, and I'm going to go to Chapter 6. Oh, no, that's not Chapter 6. Okay. In fact, this was a discussion on the 3 kinds of... Oh, I'm going to stop here for a minute. If you'll go back to the previous lesson, it says Lesson 5A. And all you have to do is click Previous at the bottom of your PowerPoint, and it will get you in Lesson 5A, which is one that I wrote. It says forces in general, friction, and systems with friction. There are only 3 fundamental forces in the universe. When I was at Florida half a century ago, there were 4. Well, we have since found that the nuclear force is really an electromagnetic force. So that has been shrunk into the electromagnetic force. The first is a gravitational force, an interaction between masses. Well, we just studied the interaction between the Earth and a small mass, like a tennis ball or a human being. with gravity, the prime example, of course. Electromagnetism is the interaction between charged bodies. If you have a charge, you also have a mass. The gravitational mass between two objects that may be charged is so weak compared to the electrostatic force. In fact, it's kind of like 10 to the minus 35 times weaker. So when we study electrostatics, we forgive the fact that the charge masses appear to be attracting. And the last force is a strong short-range nuclear, the force that kind of keeps the protons together and is buffered by the presence of neutrons. Of course, that's why in the hydrogen atom it doesn't need any neutrons. You only have one proton. And it is a short-range force. As soon as you get an electron out in an outer shell orbital, sometimes it will leave the outer, and that leaves in the element with a positive overall charge. In this course, we are only going to study the interaction between masses, or the first force. In Physics 2, we will study electromagnetism, and when we get to optics, a little bit of what's happening in the nuclear realm, or modern physics. The rest of that was about friction, and so I'm going to bypass it and go back to our next, which will be our Chapter 13. I'll give it a chance to load, and then I'm going to go to the next one, which should be Chapter 6. Here we go. I'll give everybody a few minutes to get this. You should see the storyline, Chapter 6, circular motion and other applications of Newton's laws. Interesting. Going to get into his laws again. I think I've been to Disney World too. Okay, I'm going to enlarge the screen. If someone would, maybe with your earplugs or earphones on, may want to type it out, let me know if you cannot find Chapter 6. After Chapter 13, down there in the PowerPoint connection, it is the next PowerPoint. Give you a few minutes to find it. Actually, that's not Disney World. Where is it? Oh, well. Is anybody having trouble with finding Chapter 6 PowerPoint?
No, ma'am.
Okay, I don't know who this is, but nobody's typed anything yet, right? Thank you.
I have it open.
Okay, thank you. Very good. Here we go. Well, this should look familiar. This really was the end of our study of circular motion in Chapter 4, where you were first introduced to the fact that the magnitude of the center-seeking or centripetal acceleration, A sub c, always acted toward the center of the circle. And remember, we did little similar triangles, a little discussion about you could not use the definition of the change in velocity over time the way we had used it in the kinematic equations. Note the reference to the quiz. And we found its magnitude was to take the tangential velocity, which we know that the object has, because if it had no velocity or speed at the instant it does on the rim of the circular motion, it will not be in a circle. It's going to be at rest, just sitting there. So that makes sense. Notice that they should have this velocity attached to the center of mass of the disk, or it looks like a hockey puck. When the string breaks, we note that the disk follows a straight line. Does anybody have any idea what is confining that circular disk to a circle then? Can you verbalize that? What is keeping that disk in circular motion? Because if the string breaks, it's going to travel straight. We lost some.
The tension force?
Yes, the tension in the cord, which has related to, I believe, one of your homework problems in Chapter 4, where you were looking at a position on the right and left-hand side of circular motion. That was the reason why that problem was assigned. Notice there was quite a bit of work, but it was only worth 4 points because I was after the exposure, not the knowledge necessarily. In fact, they had a small typographical error in the solution key, which I pointed out, and they have failed to correct it, but they agreed that it was a problem. By the time you rounded off to 3 sig figs, the error they made was dissolved. So I guess that's why they haven't changed it. They'd have to pay somebody to change it, I guess. All right, here's a quick quiz again. I'm going to let you bypass that, so if you want to study this, and it will always give you the right answer, so that's why I'm just going to go ahead and go on. Another one, this was what the, if you're, riding in a circle of some kind in a Ferris wheel. To really look at all of the vectors acting, and now notice that we not only have a tangential velocity that we did at the end of Chapter 4, and a centripetal acceleration, which is the black arrow here, there is now a cause for that acceleration. Every acceleration in our natural world must be furnished by a force, a net force, which means non-zero. And it has the exact same direction. Newton's second law tells us if we have an acceleration to the immediate right of a mass, then the force must have either a component or be acting immediately to the right also. We also know that if we have friction acting to the immediate left, that it is not going to accelerate as fast as we thought it was because you have a retarding force present. Well, with that in mind, they also talk about the conical pendulum. Well, ladies and gentlemen, I don't know any engineer that really deals with things in 3 dimensions. Some construction people, maybe. They do not discuss this at length. I am not interested in it. I have not assigned any homework for it, but it is interesting for those of you that want to look at it in some way. Conical pendulum, if you have a Fraunhofer pendulum, similar to one that suspended in the United Nations, it swings about the mezzanine height, and as the Earth turns under it, it goes through a conical pendulum 360 degrees every 24 hours. Interesting. Okay, there you go. A little bit of, and notice that they kind of overlap here when they discuss the equations, and then they get back to how fast can something spin. And then they have a puck or a mass that's about 1/2 kilogram attached to the end of the string. And I don't know if you've ever, as a child, had a mass on the end of the string and you started whirling it above your head, and the force needed to whirl it with a greater centripetal acceleration, which means a greater tangential velocity, and suddenly you had the string to break, which means your demand to keep it in circular motion is too high for the cohesive forces in the cord, and they will fall apart, and then it will begin to travel horizontal. And if it's horizontal to the ground, it will begin to fall, so that will be projectile motion. And they solve something here for the maximum value. Notice they said the maximum tension force is given, the length of the string, and the mass that was on the end of the string. Anybody, by any chance, those of you that are responding verbally, 12.2 meters per second is approximately how many miles per hour? Anybody? The ratio is 2 to 1.
Like
as long
30?
As, yeah, as long as you're not traveling more. Yeah, as long as you're not traveling at ridiculous speeds. A car, the speed limit's mostly 70, 75 now. And as long as you're not traveling at snail's pace. About twice that would be 24. One significant figure may be 20, but you're absolutely right. Okay. Suppose the puck moves in a circle. Well, they answer their question for you. Interesting thinking. Larger radius, it's less likely to go flying off at tangential straight line motion. They go back to their car scenario and they said, why can a car turn in a circle? Now, if the road were frictionless, try to turn in a circle. I don't know if any of you have seen somebody try to make a turn on an icy road or an icy lake or something. We don't have that stuff in Florida. We don't have that kind of experience. But if you try, if it's totally frictionless, you're just going to keep on traveling straight. In fact, if you're in a car, the only thing that changes the direction of your car is your steering wheel. The actual push off the axle of the rear of the car is all forward. The back wheels do not move in most cars. It says if the radius of the circle is 35 meters, that's roughly 17 feet. That might be an outer lane of a turn of some kind to the left. If the coefficient of static friction between the tires and drier pavement is 0.523, ladies and gentlemen, this is low for a car. Does anybody remember when I talked about friction, and I believe it was in one of your homework problems that I assigned for information only, is it possible to have a coefficient of friction greater than 1? Anybody? Yes. In fact, the manual to your car, if you have one, you may want to read through it. My manual says that on a dry pavement, usually concrete, the coefficient of friction between the stock tires on my car was 1.1, which means the road is helping me stop. And that's what I want. I don't want my brakes to burn out every time I use them because the road's not helping me stop. Okay, so this is a very low value. This might even be a pavement that has been run very smooth for some reason, usage. Notice that the frictional force, the view of this car here is from the back, and they're getting ready to make a left-hand turn. They need to say that. We're looking at this car with a normal force that equals its weight, N, they use little n, and its weight, mg, and the frictional force then is moving to the left. The car is going down into the page. The left-hand turn is going to be out of your field of view, making a left-hand turn, as if you were a car behind this car. The frictional force, by definition, of course, and notice they have a sub S on that mu value. The reason is the tires are not slipping forward or backwards like a bowling ball sometimes. The molecules of the tire are making static contact with the earth. The wheels are not spinning. To distinguish the coefficient of static friction, contact-to-contact molecule, to kinetic, a small s is used to tell you what is happening. Obviously, the frictional force is V, and notice they say max, or tangent, squared over r. And a little analysis of the y component, which to me is redundant. From the diagram, can everybody agree the normal force, if drawn, the same lengths with respect to the center of mass of the car, they would cancel anyway. A free body diagram was not asked for, so it is really not needed now. And of course, solving. Notice they have the equation, they have a substitution of the numbers, and then they have an answer. Now, according to our rule of thumb, this car can make this turn traveling approximately how many miles an hour? Whoops. What was our rule of thumb? Let's say 26. I don't know if you've noticed, but a lot of times when they give you a sign recommending a speed limit around any kind of turn, it's usually around 25 miles an hour. interesting. Sometimes that's more than you need. I hope it's not less. And it might be exactly what you need to stay moving in your circle. Interesting enough, suppose a car travels this curve on a wet day and begins to skid on the curve when its speed reaches 16 miles an hour, roughly. What can we say about the coefficient of friction? This is finding the coefficient of friction kind of going backwards in the equation. Whoops. All right, there you go. And you find that it has diminished by 0.2 compared to about 0.5. And that is typical of anything that lubricates the road. It's even a little less if you've had motor oil or some kind of oil. And, of course, that's why when rain starts, rain, of course, is more dense than the oil. The car can become hydroplaning off of the oil that is seeping to the top of the rainwater on the road. And so you really need to slow down when it begins to rain. As the road gets real wet and the oil material begins to slide off, usually roads are slanted. If anybody wants to work as a traffic engineer, the grade can be as low as 1/10 of a degree, and the oil will begin to drain to the side. Here is the bank roadway. Interesting enough, there is a whole course on bank roadways. Daytona Beach Speedway has a banking that's 33 degrees. That's about the limit. Because as a tourist, I climbed up there, and you get a little tired trying to climb up a 33% grade. Your text has an interesting presentation, but I generally do not do this presentation, and I wish that I did, but I'll tell you the reason why. Notice that the weight of the car, which is vertically down, the normal force is at the angle of elevation, and that so confuses students throughout the course that I have elected not to cover the information. It's so that you can reevaluate normal forces when you're on an incline and you're going up and down the incline, not using it as a banked curve. The motion in the bank curve is to maintain a radius of curvature. The motion up and down an inclined plane is to go up and down an inclined plane. That's not the purpose of a banked roadway. So moving right on. Okay, give you an equation. Okay, talk about it talks about G changing. Well, that means G would change in the equation. Interesting discussion. What I am interested in is a vertical circle. Ladies and gentlemen, we're going to be developing an equation which really relates a little bit to the elevator motion, which we did not cover, actually in the interest of time. But it's not exactly like it, because the elevator only goes up and down. A vertical circle is like a Ferris wheel. It is rotating perpendicular to the ground. That's not what an elevator does. Notice that they talk about a child moves in a vertical circle. The radius in a vertical circle will never be changing for us. And in this particular case, has a speed of 3 meters per second, and they have the 2 red vector arrows that imply the direction of the speed is continuously changing. Determine the force exerted by the seat on the child at the bottom of the ride. Express your answer in terms of the weight of the child, namely mg. Next frame. We want to look at the vectors of force acting at that location. And notice the weight will always be acting because we deal with masses very near the surface of the earth. And it looks like the normal force here has the same value or has been drawn with respect to the center of mass of the seat child system, but it's really longer. Because if it were equal, this child would not be in circular motion. And we observed that they were. They were in a Ferris wheel. They had a tangential velocity. They have a tangential velocity and there's an R. Some kind of force has got to sustain the circular motion. And I think someone told me that that would be a tension in the string or a tension in the metal connection of the Ferris wheel car to the actual hub of the Ferris wheel. So we will look at these forces. Actually, the normal force has got to not only lift so that you will not fall out of the Ferris wheel, it's got to lift itself to provide a value that's larger than the weight, which means when added to the weight, would provide then some kind of centripetal force. That's what we're after. A normal force here being somewhat greater than the weight. Well, determine the force exerted by the seat on the child at the top. In this case, we notice that a component or part of the weight is now furnishing the centripetal force. And so we have its weight minus the normal force of the seat. And of course, they finish with the calculation. It says, suppose a defect in the Ferris wheel mechanism causes the speed of the child to increase to 10 meters per second. What does the child experience at the top of the ride in this case? Actually, he's going to be moving faster than the acceleration due to gravity. The seat is going to fall out from under him faster than he can keep up with it, so he will lose contact with his seat. Has anyone experienced that at all? Actually, this is the principle behind, I don't know if you know that during astronaut training, they put them in a huge Boeing, I don't know, bigger than the 767 of our first quiz. They pad the inside, there's no chairs, and they make a vertical circle, and while this Boeing airplane goes through the top of the circle, the plane is going to have an acceleration, centripetal acceleration, greater than the acceleration of 9.8 meters per second squared, and the people begin to experience weightlessness. I'm sure you've seen pictures of astronauts that are floating in the fuselage of this huge Boeing, and they make somersaults, but they're very careful to try to not collide with one another, or the top or bottom. They wear helmets because you can injure yourself when the side collapses with you. I don't know if any of you have ever been to the Tower of Terror, which I think is at Universal Studios, where you go to a ride that's on the top of the tower, and it will fall faster than the acceleration due to gravity, and you're told to, of course, wear a seatbelt, and you feel like you've levitated out of your seat. Well, I wore a loose hat with a chin strap, and I went through that 5 times before Ladies and gentlemen, I don't know if you can hear me, but my phone turned off. Can anyone hear me?
Yeah, I can hear you.
I can hear you
Yeah,
now.
it went dead. I don't know. I think I know where it went dead. I was talking about I was wearing a loose hat on the Tower of Terror, and I went through the ride 5 times because I was trying to get them to take a picture of my hat suspended above my head when my seatbelt forced me to accelerate faster than the acceleration due to gravity, and my hat had to catch up. And as soon as the chin strap hit my chin, of course, it was pulled back into the system that was moving faster than the acceleration due to gravity. And in fact, that particular ride will do that about 2 or 3 times before the ride is over. And of course, everybody's just thrilled with it. A similar phenomenon appears at Frontierland, where they have the train that goes through parts of Frontierland. They go up a vertical circle and down, and of course you have this bar that keeps you in the seat, and everybody's kind of plops down in the seat as they come back and meet the train platform. So a lot of these concepts are incorporated in rides that you will have in entertainment centers, that kind of thing, as a matter of fact. Okay, here we go. For those of you that are curious, in Chapter 6, I am only interested in frames 1 through 41. The discussion of retarding forces is empirically derived. Does anybody know what I mean by empirically derived as opposed to theory? Whoops. Empirically derived means experimentally determined, which means you just do some things by trial and error as opposed to using theory to derive an equation. You use laboratory experimentation to establish an equation. Okay. Of course, this is it tells
Sorry,
you.
what was that? 1 through 41?
Yes, sir. So we
Okay.
got a little. Yeah, we got it a little bit. So, you had a problem on your last test with respect to non-uniform circular motion, where you had not only a tangential velocity, a centripetal acceleration, but now you have cars on the rim that were accelerating or decelerating. And notice that you determined a net or total acceleration in that test. And now we know the source of that force, which is illustrated in this particular frame. And here's one of your quick quizzes. It's just saying draw the vectors, a study of what's showing you the centripetal force in each, which is drawn purely by construction, since you know it's somewhat curved at a maximum and minimum here. And then, of course, they ask the same question. And here's where the possible resultant force would be. No wonder A is going down, and it looks like C is getting ready to go up, according to the dark blue resultant forces. Here's another example of a sphere or a ball attached to a string executing vertical motion. And they have identified the vectors in velocity vectors in 2 positions. They have taken an angle with respect to the vertical. And notice that theta here in the equation is measured from the vertical, not the horizontal, which is by custom. Every book does it, not just Survey, because it looks like the pendulum arrangement, of course. But there's enough tension to provide circular motion, not just a pendulum. It has quite a bit of tension to get through the entire circle. Notice that in the third quadrant, we have a component of its mass acting anti-parallel or toward the lower left hand, and it has a value of mg cosine of theta. Looks a little like an inclined plane equation, and it is very much similar. And it has a component tangential in the direction of motion at that point in time, not continuous like the inclined plane. And they notice that the component that opposes the tension in the system of the sphere certainly is going to, by the summation along that direction, diminish the centripetal force, which means you might want to have a greater tension or swing it faster. A way of looking at that is with respect to our Ferris wheel. Again, going back to the concept, the Ferris wheel was going clockwise, like the hands of a clock. The illustration to the left is going counterclockwise. That was the purpose of this frame. And the analysis is the mirror image. Okay, notice that the tangential force, because it's straight line with the tangential velocity, is an application of Newton's second law. Notice that if we take the tension minus that component of the weight that diminishes the tension, what's left over is the centripetal force, the mv squared over r. If you are asked to determine tension in a homework problem, you may use the equation that has been blocked off, equal to t, of course, with impunity, since we have discussed the meaning of that equation. Here's an example of the tension at the top, and notice the tension at the bottom, where the weight, and if there's any tension in the string, is going to constitute the centripetal force. Notice that centripetal force is embedded right here, and it still would equal T bottom minus mg. And notice if you take part of the T away from mg, that's what's left over, following your algebraic expression. What speed will the sphere have if it passes over the top of the circle if the tension in the string goes to 0? That means just like the child at the top of the Ferris wheel, they were leaving their seat, just like the seat leaving you in the Tower of Terror or the Frontier train thing at Disney World. Notice that this tells me that the velocity at the top is related actually to whether or not you are experiencing an acceleration in the radial position of g, which is the defining factor. If it were greater than g, remember that impossible condition. If it's less than g, you're not in free fall. Okay. And it says the ball enters free fall from the part of its motion near the bottom. It becomes slack for just a very small period of time. Okay, we just kind of talked about that. This is motion in acceleration frames. The frictional force in an accelerated frame sometimes is viewed as why the motion is occurring, but it's only an apparent force that seems to act on any mass described in an accelerating, non-inertial, they misspelt the word. I haven't caught that lately. Frame of reference. Real forces always interact between how many objects? If you have a force in an inertial reference frame and you have cause effect, you are dealing with at least 2 objects. When we're dealing with friction, remember the friction that was a centripetal force? We did not look for, because of circular motion, a reaction to friction. You didn't see any reaction to friction in your vector diagrams in our previous study. Think about that a minute. Which kind of answers the second question in the quiz today? Which of Newton's laws are applicable to, I forgot how I worded it, inertial reference frames, or which 2 of Newton's laws are not viable in a non-inertial or non-classical Newtonian frame of reference or system? Does anybody remember what I said when I talked about the three laws and said there's a limitation on these laws? Uh-oh. That concept permeates two chapters here, circular motion and universal gravitation, which obviously, if we consider the orbits perfectly circular, which they're not, is one reason why Kepler was discussed, which we're not going to cover. The answer to part 2 of the quiz today was his first and third laws are not applicable to accelerating reference frames. Accelerating reference frames are non-inertial reference frames. Accelerating reference frames is the general theory of relativity. When you study relativity, it's usually the special theory of relativity where your reference frames are inertial, the velocities are constant, there is no circular motion. So when somebody tells me they understand all there is about relative motion, I'll say, are you talking about the general theory, or sometimes referred to as the Galilean relativity? Okay. Let's look at what happens when a person is experiencing circular motion. Notice that A is a frame showing a car, and it looks like we're in a helicopter hovering over the car. But if we were sitting behind the person, or even if we were sitting in the car, we're going to experience the same force in the car's reference frame. If you're moving with the same velocity and the same centripetal force as your car, you are located in a system where your velocity relative to the car is zero. That is the easiest defining definition of inertial reference frame, which means Newton's first, second, and third law apply to inside of the car. If you were blindfolded and you didn't feel the pushback of the door when you're trying to take a circle, you probably wouldn't know you're going in a circle. When the car begins to execute a left-hand turn, how many notice that generally, even with your seatbelt, your body wants to continue to move in a straight line motion and will push against the door or your seatbelt? That pushback is a consequence of you pushing on the car, and it's pushing back. If your seatbelt was malfunctioning, and if the passenger door had been removed, you know, those beach buggy type things, and somebody were making a left-hand turn, you might have slipped right out of your seat, going straight, and landed right in the middle of an intersection, because that's where you'd be if you were making a left-hand turn. That has actually been known to happen before cars had seatbelts. And some of the cars, because we're in Jacksonville, we have beach buggies, and some cars did not have a passenger door or rear doors. I believe the law required that the driver have a door, and sometimes they removed it when they got on the beach. So this has been known to happen. Incidentally, where is the safest part of an intersection, ladies and gentlemen? Let's say it's 4-lane, 4-lane, and 4-lane and 4-lane. Where is the safest part of an intersection? If you've ever noticed, in the exact center of an intersection, there are pebbles, sometimes broken glass, that finds its way right in the center. If people make an appropriate turn left, all this debris will kind of fall in the exact center of the intersection. Next time you make a left-hand turn at University and Atlantic Boulevard, notice all of the debris that's in the middle of that intersection, ladies and gentlemen. Okay, let's go to the next one. This is a discussion of when you're throwing a ball to a friend and they're on maybe some kind of moving disc, and by the time it arrives at them, the ball appears to be located elsewhere. The best way to view this is when you first throw the ball in the left-hand frame, you want to throw it straight to them, and yet you moved a little bit and they moved a little bit, and the ball appears to be curving. That's because you're looking at it as sitting on the disc. Kind of interesting to look at that. Sometimes they would have that in carnival until somebody could throw it fast enough, they hit the person. So can't do that anymore. Some quick quiz material here. If you want to go through it, it kind of reinforces some of the facts of what is happening. The 39, fictitious forces in linear motion, another observation there, and the angle that you see when you're going in one of those mad tea party type things that you see at Disney World with the little kids and whatever, twisting and turning. And here are again frictional forces in linear motion. Linear motion that relates to the fact that I have to obey Newton's second law here, and of course we know that that's not going to be true. I only need one force in accelerating reference frame. There is, at the end of this literature, way at the end, and I forgot what frame it was, there are 10 problems or questions. And give me a minute, I've got to clear my throat, and maybe I could find it then. Okay. In frame 55, if you would like to enhance your homework problem or homework score, please go to frame 55. There are 10 assessment learning questions that are not answered. This one and the second one on page 56, and I believe even 57, are already related to a question you had in homework associated with the circular motion in Chapter 4. You have some background. Feel free to answer any or all of them, but make sure that you can justify one of these answers, and notice it says impossible to determine. And make sure you tell me the data that you're going to use, and most of it's the moon or the earth. You can extract that from a resource, I believe it appears on the inside leaf of your textbook. And make sure that your problem solving is in at least 3 steps. These problems are worth 2 points apiece, so you're looking at 20 points to enhance your homework grade. And of course, divide that by 2, and you realize that is 10 points.
Sorry, what problems are you talking about?
They begin with frame number, wait a minute, back up, 55. Frame
Okay.
number 55 through, I think, 64 will be what they call assessing to learn. They don't give you the answers, so you can get it wrong, but if your approach was right, I'm a methods teacher, not a right answer teacher. Just shows me that you can put things, make sure you show your work, that the problems are in 3 steps at least for all of them. Okay. If you would like to take a break, ladies and gentlemen, I'm going to be calling up some material that is going to serve to look at some of the content of Chapter 6, and that would be one of my lessons. So just take about a 5-minute break, and it should be lifted immediately. Well, give it a little time. In Canvas, I don't think anything's immediate, unfortunately. Good. I believe it's about 1 minute before I'll begin again. Okay, ladies and gentlemen, if you have earphones on, you may want to just type, yes, you can hear me, and I can pick up on it when I check attendance again. If not, somebody want to give me a shout out that you hear me?
Yeah, we can hear you.
Thank you, and I believe it's been 5 minutes. So this lesson that I made out a quarter of a century ago is only 11 frames, but it serves to clarify some issues. Some of the wording may seem familiar because I shared this with the publisher of your text during the 6th edition. So just bear with me. We're going to get a little repeat. In circular motion, either uniform circular motion or non-uniform circular motion is always a tangential velocity. Yep. And a radial acceleration. Yep. You realize in our previous lesson, they didn't say that. They showed it in a vector diagram. What caused the radial acceleration? Well, it's a centripetal force. Applying the second law into the equation for the acceleration, remember they got the magnitude as m sub v tan. Remember, I like to use the word tan to imply circular motion, velocity on the rim, straight line, over r. And now I have put the reference r because I have a vector notation for the centripetal force. Centripetal force is not one of the fundamental forces, and that was sort of implied. Therefore, it must be divided by gravitational forces or electromagnetic forces or nuclear. Wow, we only study gravitation, so we're lucky. Consider a car making a left-hand turn while traveling with constant speed. Notice that my diagram is from above, as if we were hovering over the diagram in a helicopter. And notice that we derive the same equation of V static, V sub S, times the normal force equals V sub tan squared R. A little bit different notation, but I think it's a little clearer. Then we kind of look at the coefficient of friction as being the force that has been applied. That suffices for our F sub C. There's a gravitational interaction between the wheels of the car. In fact, we have 4 wheels, and if the car were 400 newtons, each wheel is supporting about 100 newtons if the center of mass was located in the geometric center, which is what we assume is happening. Most of us know with the motors in the front, the center of mass is toward the front of the car. And notice that since the mass of the car can be canceled out, it makes no difference how large or small the car is. It's going to be canceled out. This is important if you're talking about banking curves. You don't bank curves for a particular kind of vehicle. The curve effect is the same for motorcycles as it is for passenger cars, as it is for semis. Unfortunately, we don't study it my choice there. But believe it or not, blank curves is not mentioned as part of the mandate topic for the state of Florida. It's separate because of its motion and the uniqueness of the normal force. Here we're talking about the vertical circle, and I start with the 2. And notice I have to label the angle A. They didn't have a theta. And the 2 forces that are acting on a ball that is moving in a vertical circle. Well, we saw these before, but they didn't start with this simple design. They started with components and stuff. And now I've got the components, and I noticed that the centripetal force in red is indeed the tension that has been diminished by the weight of the suspended mass on the string because of its component. Any vector can be broken down into 2 components. We deal with components that are mutually perpendicular. And notice that that is illustrated in this diagram in the kind of pinkish component that appears to be acting toward the lower left and the weight component that appears to be acting to the lower right. That is almost identical to their vector diagram, except since I have the components of the weight, I have got to squiggle out the weight or erase it. It should be there so we can see where the components are. And notice W sine of the angle A really opposes the direction of motion if it's going up, and it provides the tangential direction of motion if it's going down. Again, the equations were derived, and in this case, I like to concentrate on the right-hand expression as being the centripetal force. Let me back up there, got too eager. And it equals W minus the weight cosine of the angle. I like this expression for tension, centripetal force, and weight component better. I will remind you, at the top, the cosine of the angle at the top of a vertical circle's motion. Does anybody know what angle I'm talking about at the top? In other words, the cosine of the angle A will be the cosine of what degree? Uh-oh. I hope some people are typing 180 degrees. This equation fits for all angles, even when it's at the bottom, because the cosine of 0 degrees is what, folks? Uh-oh. 1. When it has gone through a quarter turn, which was similar to some problems you encountered in circular motion, the tangential force is at 90 degrees to the weight. So if you put the cosine of 90 degrees here, you just get the tension equals mv sub tan squared r. This equation fits 360-degree values a little more directly than our previous discussion. Here, and unfortunately the vectors in color, I'm going in the plane of the paper, and notice I have 180 degrees. I have the centripetal force that's red acting down as a result of the tension force and the weight. And of course, I put it in my equation. I use 180 degrees. The tension is less because the weight can provide some of the centripetal force. Recall tension in the elevator problems, which we don't have. Actually, this statement, the tension is less because the weight can provide some of the centripetal force. That happens in the International Space Station. It happens as you circle the Earth as an astronaut. Part of your weight is used up to provide the centripetal force. If enough of it needs to provide the centripetal force, you become weightless to the limit. That's why you appear to be weightless. All of your weight. Huh? Did someone say something? Hello? Hello?
I didn't hear anybody say anything.
Oh, thank you. Maybe I'm going crazy here. Somebody said -1, but it may have been someone else. Thank you. I'm not crazy. I swear I'm not. All right, here we go. The vertical circle, and And this talks about being weightless, etc. And notice that at the centripetal force, if this bottom equation, if the centripetal force is 0, that will mean that the m's go out, and then g equals the centripetal acceleration. The condition on this frame, 8, is the equation that yields g is then equal to the centripetal acceleration. It is all used up. You are now in free fall. And consider the vectors at the bottom, and of course this is to the left are the vectors at the bottom. Notice that the weight is down, the tension's up, and whatever's left is the centripetal force. And a little bit of notation at an angle other than 0 or 180 degrees. And actually, and of course, to remind you that the angle is measured with respect to the vertical. Here's that 90 degrees I talked about, and the tension then is just m relying on the tangential velocity. Already mentioned that. And the last frame has, it says chapter 5, but that was the 6th edition. We're now in chapter 6. They added another chapter for Newton's laws at the time. So if the last frame of any of my PowerPoints may be a chapter off, if you want to just remind yourself that the last frame of our lesson for circular motion really is referring to chapter 6. And I'm going to move on now to our last portion of the lesson today. And I want to make sure I get lesson 690. So I'm going to be traveling here for a minute. And nope, don't want to do that. Next one, here we go. My lesson 6A, which will augment a little like our previous augmentation of our study in chapter 6. This lesson is 6A, and remember it was a chapter behind. This really is associated with chapter 7. And notice that that was a reference that I gave it in the lesson outlines, I think. Our study of work, which is a fancy word for mechanical energy. Work is going to be defined as the people working in science define it. I will talk a little bit about the work being done by physiologically about muscles, but that is not applicable to physics, mechanical engineering, or anything that's external to the human body. I will particularly be talking about the first of two kinds of vector multiplication. And they call it the scalar product or the dot product, as we will see why in the notation. I have a disclaimer here. In fact, the study of energies and work and all forms of energy at our level with gravitational forces is a very large chapter in some books. Your text has chose to subdivide it into a study of physical work and gravitational potential energy, which is the second chapter, and conserved energy field. So this lesson does not replace the discussion about work, energy systems, etc. given in the text. This lesson augments the text presentation and examples. Work in physics is not defined the same way as work done in everyday situations. In order for work to be done in physics, a force must be acting on an object or system, and that force must have a component acting in the direction of motion. This last sentence can mean several things. First, motion is occurring, therefore a displacement takes place. I think you agree with that. If you went from one place in your room to another, motion occurred. The object is located from some initial reference, usually we set that equal to 0, to some final position from, say, R initial to R final. such that, and this should be a delta in front of R equal a value, if you went back to your original location, it'd be 0. The difference between distance and displacement again. The force is acting in a direction of motion, or at least has a component acting in the direction of motion. Now, this is getting a little restricted here. And quantitatively, work should depend on force or its component in a system. And I think the bottom line here has been marked off. So I'm going to go to the next frame because sometimes I'll repeat what the frame had. Whoops, 6B. Nope. Did the wrong thing, folks. Let me back up. That's our next lesson. Let me go to the full screen then. There we go. Quantitatively, work should depend on force or its component, which is force times the cosine of the angle. Recall that from a problem on the last test. And some change in R, which will be dependent on the angle the force makes with the real vector or force that's been applied. Next. Okay. Does anyone recognize this particular diagram with respect to your last test? Yoo-hoo! Can you still hear me? Hello?
Yeah, we can still hear you.
Yeah, I can hear you.
Okay. Does
It takes a
anybody
second to unmute.
Pardon? Pardon? Okay.
It takes a second to unmute ourselves.
Okay, thank you. I'm rushing a little bit because I'd like to get to a certain location today, and we did spend some time in administrative tasks. Just slow me down, although I don't add very much to what I've already written, as you probably noticed. This was similar to a problem that you had on your last test. And it was by design, because I want to relate concepts you should be learning. And how many of you remember the purpose of my test is to see if you can use what you're supposed to know. I'm past testing to you whether or not you know it. Can you use it? It's going to be the important concept in your life as an engineer in whatever field you go into, including medicine. Notice that I have identified only the horizontal component. The work, then, is that force applied times the cosine of the angle that it made with the horizontal. We're back to the horizontal angle. And notice that I have implied the separation distance to the right with the final x divided by the initial x. If we set x sub 1 as our reference 0, we can just summarize that as the work being done as a force, the cosine of the angle it makes with the horizontal, and notice how it is measured. Usually, well, an acute angle, times the distance that it traveled. And it becomes more than just a displacement. Of course, x implies the direction. Another way of saying this is F cosine of the angle is the projection of the force onto the direction of motion as observed. Oh, very good. Off we go. In the upper right-hand corner there, it mentions the units. Notice the force times the distance is defined as a joule, which is a capital J. It usually has a top to it. This almost looks like the JS component, but it has no vector over it. It's not boldface. In the CGS system, the force is in dynes, which is about 100,000 times smaller than a Newton. The weight of a mosquito is about 1 dyne. That's why we hardly ever use it unless you're in medicine. And then it moves, for instance, if a mosquito were to fly vertically upward 1 centimeter, that mosquito has done 1 erg of work against gravity. Here we go. From the equation, if no force acts, there is no work done. And if no displacement occurs, there is also no work done. The last part of this statement needs clarification with respect to our everyday experiences. In other words, the real world. As an example, consider someone holding a brick with outstretched hands or arms. The brick remains at the same height for many seconds. You are applying a force equal to the weight of the brick to support it against its own weight, but no physics work is being done. Physiologically, the muscles in your arms are flexing, relaxing about your elbow, which is really the fulcrum of the torque, as a pivot point. You know your muscles were flexing. Sometimes you can feel them, because as soon as you release the brick and lower your arms, the muscles feel sore due to the lactic acid built up physiologically. In this example, no work in physics is being done. But if you're in physiological kinesis, you will study compressions and thrusts. When you press against the wall pushes back. If you go into construction engineering, civil engineering, you will study these compression thrust forces, a little like what is happening inside of your arms when no physical work is being done. So if you plan to go into civil engineering, you've got a whole other course to go through with respect to internal forces, which obey the third law, Newton's third law. Here we have at x of 1, we look at the fact that the velocity has a 0 value, just to kind of start out. And we observe some acceleration occurring, which then implies that we're at a different location that was greater than 0. If our reference was to the left, it would be positive. The acceleration is certainly greater than 0 in the positive. So the equation and the direction of motion sort of tells us what signs and how to apply the variable. The next talks about something that the book talked about, a push down on the mass. Notice has no direction with respect to the implied direction of motion. There's no motion occurring unless you have a component of the force acting. Just because you press down on the top, it doesn't mean it's going to stop it unless you press so hard that friction overcomes the implied force. And that's what happens here to the right. When the net force is equal to 0, the applied force and the frictional force will cancel, and the acceleration becomes 0. Also, notice the velocity remained constant while I was pressing down on it. Another way of looking at the situation is to realize there is no net force, therefore no acceleration in the direction of motion. There is no projection of a force in the change in x direction. And the angular dependency on work also implies this. The direction of the motion that was occurring when you applied the vertical force is 90 degrees. The cosine of 90 degrees is what, ladies and gentlemen? 0. 0 times the change in the position is going to be 0. Since force is a vector and displacement is a vector, now, ladies and gentlemen, this is about as far as I wanted to get today, so I'm going to start going slower. The work equation, and I finally found what I thought was a symbol for the angle, and here's the change in a position. Could be 3 dimensions. The force can be 3 dimensions, I, J, and K. The final position can be I, J, and K. The initial position could be I, J, and K. Work then is defined as taking the force times the cosine, which is represented by a dot, to save you a little bit of notation. In fact, this dot should be a little larger. Times the change in position. This implies that a constant force was acting as the object went from position R1 to R final. And let me remind you, it could have gone to the moon and back, and the initial position and the final would be the same as if it went straight from the initial position to the final. So work doesn't tell you a lot. these last expressions are called the scalar product, the dot product of two vectors. I don't know how many of you have already taken maybe Calculus 3, where the concept of the dot product and the other type of vector multiplication has been managed there. I am assuming that no one has had that lesson or lessons, and so I'll be teaching it as we apply it to physics. Note the right-hand side of this multiplication of vectors contains magnitude values. Notice this should be an absolute value for force multiplied by the absolute change in R times the cosine of the angle. This is the way it works. It works. The dot product then should produce a scalar quantity. In other words, no direction. The scalar product is commutative. You could take the change in R and multiply it by F, or take F and multiply it by R. And the distributive property of multiplication applies. This last property is illustrated by considering one force, F, which is constant, and two sequential displacements from R1 to R2. Your book lets the initial position be 0, 0, 0, which is very restrictive. In the real world, rarely do you know you're going to start from 0, 0, 0. It looks good on paper, but if you're out in the field, you may want to take a GPS bearing. To illustrate the dot product by determining work in physics, go to the next frame. And here's where I really want to take a lot of time, particularly if you have never had to take a dot product. Here we go. Let's give some values. The equation, let's define the force as a 3, 4, 5 triangle in space, and the final position being somewhere in space, and the initial position being somewhere in space. I would hate to have to determine the amount of work that a spatial, say, spaceship was taking, or maybe a child in a toy car of some kind, and how they'll go from one position here to the other, applying the same force on their paddle wheels or something. First, we have to determine the change in R. Well, the change in R means the final minus the initial. Look at what I have here. I have the final 6i plus 4j plus 3k minus the initial in its parenthetical statement, because I don't want to distribute the negative yet. However, with all of these positives, it would be easy to forego the parenthetical parentheses and just write it as minus 5i minus 5j minus 9k. You had a homework problem in Chapter 3 that did just this. 42i minus 1j. I graded so much homework, I think I have it memorized. Notice the value here is 1i minus 1j minus 6k. I hope I did the arithmetic right here. Check it. Work then to move to the second expression for the equation would be the force in vector notation, minus 3i plus 4j minus 5k. Notice I brought the units in because it's not integral or differential calculus. There's no quadratics or cubic functions. I could have placed way over to the end next to the meters. Notice I have the dot product instead of the cosine of the angle between all of these quantities. And then the parenthetical statement for the change in R, which was 1i minus 2i minus 6k in a parenthetical statement. Excuse me. This expression can be viewed as one trinomial in algebra multiplied by another through the dot product, which means when I distribute the first term of the first trinomial through all of the terms of the second trinomial, I need to add the cosine of the angle between the directions. Should I repeat that, ladies and gentlemen?
If you could, ma'am.
Yes. This expression can be viewed as one trinomial, just in algebra, multiplied by another trinomial. This is pure just algebra. This is probably college algebra, but I know some advanced algebras in high school deals with unit vectors. So our work was minus 3i plus 4j minus 5k times the cosine of the angle between the unit vectors, not the numbers, the unit vectors, and then delta r, which was a plus 1 minus plus 1i minus 1j minus 6k. And I brought all of the units over to the right. I know that equals a joule, but right now it doesn't make any difference. Now, let's expand one trinomial multiplying another. I wish I had access to my pointer here, but focus your attention on all of the, well, it should be black. The minus 3 times 1 times I. The minus 3 is a coefficient in front of the first I in the trinomial just above it. The 1 is the coefficient in front of the first term of the second trinomial. That is the process for multiplying a trinomial by a trinomial. I have brought the direction of 3 to, I move through the numbers, which you can do since numbers are just scalar, but keeping the 1i in front of the I for change in R. So I have an I, and that dot should be between the two I's. We find that the first I, when projected on the second I, is really in the same direction. So the dot product here means a cosine of what angle, somebody? What angle if I take the unit vector I and I project it on the unit vector I? They have a relationship that's the same, and the angle between those two lines running along the x-axis is 0 degrees. What is a cosine of 0 degrees? Very important. Yes. So expanding the first terms of the two trinomials has really yielded, after considering the cosine of the angle between the two unit vector directions, has become a minus 3. No direction, just a minus 3. Let's go to the second term in the first trinomial. 4j, first term in the first trinomial to the second term in the second trinomial. What have I done? Let me go back. I got you. Blue is coordinated blue. Black is black. I'm the one that wrote this. Let's go to the minus 3i that's in black now. So I want to add minus 3i, multiply it through the dot product to minus 1j. That will be the second term that's in black, 3 lines from the bottom. I'm sorry I confused you, ladies and gentlemen. It should read, open parentheses, minus 3, close parentheses, open parentheses, minus 1, close parentheses. The minus 3 had a direction of I, the minus 1 had a direction of j, and that dot should be between the two. The dot between I and j means I, cosine of 90 degrees, j. That tells me, is there any direction of the work in I, cosine of 90 degrees, j? First of all, what is the value of the cosine of 90 degrees? That would be your black vectors there. You're right. So if you take I and dot it into j, actually if you take I and dot it into k, This was also on your first test. If any of you remember, the answer to that unit vector question was they're all at 90 degrees to one another. You got partial credit, however, if you mentioned that the unit vector could be equal to 1. But you can determine what your unit vector value could be. And in astronomical terms, it many times is in billions and trillions. So the best answer there, I think, depending on your test version, was either A, and I think it could be F, I think, or something like that.
So it's 90 degrees if it's one vector to another, and then 0 if it's to itself?
Well, no, you're saying that it has a magnitude, but it has no direction, so no work was done. The magnitude is 3. But remember, direction plays a part in whether or not work is done. And the two vectors are at 90 degrees. Remember when we were pressing down on the block? It kept moving, but it didn't change direction, didn't change acceleration. And if I press down hard enough, friction then gets large enough that it's going to stop the system, which means I'm doing work against friction, not on the block. If I take I dotted into J, that value is 0, because the cosine of 90 degrees is 0. Anything multiplied by 0 is going to be 0. Let's look at the last term. When I take the first term of the first trinomial and distribute it to the last term of the second trinomial, I will get two parenthetical statements, -3 and -6. Okay, that's plus 18, but I have I, that dot should be between I and K. What is the dot product between I and K? What is the dot product between I and K? Remember, the dot means the cosine of 90 degrees. I've just found another value of this vector multiplication that has no value. Cosine of 90 degrees for that third term to the right that is purple is 0 again. I think I see a trend here. Go down to the red vector now. As the second term of the first trinomial is being multiplied by the first term in the second. And we get 4 times 1. J, always keep that unit vector first, dotted into I, although you could do I dot J. What is J dot I, ladies and gentlemen? Come on, what was the answer? A lot of you got that answer absolutely right, or you certainly got partial credit on it. I didn't even have to see your work if you answered it with respect to two possible answers. I knew exactly what your selection meant. So I didn't have to see any work for you to get partial credit in that particular case. What is the angle between J, unit vector, and I? Come on, folks.
90 degrees.
I know you know this, and I get only one person. Of course, I'm assuming that a lot of you are on mute. I understand that completely, ladies and gentlemen. I know a lot of you are on headphones, and that's a good idea if you have a dog, and I have this experience, but we've found out a way of maybe keeping them quiet. I hope they remain that way. Absolutely. Well, let's go to the green term. The second term of the first trinomial multiplied by the next in the second trinomial. The 4j multiplied by -1j. The coefficient is -4. But when I take a vector and dot it or project it on itself, remember the angle was 0. The cosine of 0 is?
1.
Yep. Well, we found the next term. The first term was -3. The second term, or -3 joules. The second term is the green term, which is -4 joules, if I were to put the units in there. Now, let's go to the light blue term, which is taking the 4j, actually it looks like it's pointing to 5k, but it's really 4j multiplied by minus 6k. And that dot should be between the j and k. Wait a minute. These unit vectors are different, which means they must be at what angle? The cosine of 90 degrees is 0.
0.
So that light blue term is another no work done to go from J to K. No, that's 90 degrees, it becomes 0. All right, back down to the blue, which is the third term of the first trinomial. Bear with me. I hope I haven't put anybody to sleep yet, but there is a reason why I'm doing this, ladies and gentlemen. I'm looking at all 9 terms, but I'm sure you can predict which of the last 3 are 0 and which of the last 3 is not 0. The first blue term is minus 5k times 1i. 5k, plus 1i, which is the third term of the first trinomial and the first term of the second. Well, I've got k dotted into I. What do we know about that dot product? It's going to be equal to
0.
somebody. Yeah, I think somebody said 0. How about that last term, the 8th term? This is minus 5k times a minus 1j, which is the last term of the first trinomial multiplied dot product type vector multiplication of the second term. Well, k dotted into j is also 0. How about this last term? The last term of the first trinomial, minus 5k, dotted into minus 6k. That dot product to the far right should be between the 2 k's. We just learned that the angle between any 2 unit vectors that are the same is going to be 1 in our basic definition. So the last term would be 30 joules, or newtons per meter. I think you can realize that of the 9 terms, we ended up with 3 non-zero numeric values, which I think 2 of them were negative and 1 of them were positive. So we can begin to add them algebraically. Here's some expression for the cosine. I didn't want to project it yet because I wanted to keep repeating the cosine. Is it 90? Is it 0? But here's what I was talking about. And notice the work then is first product was minus 3, the 0, 0. The second term, our second line was minus 4, then 0, 0, 0. And then we had the 30 Newton meter. The work being done, whether or not I went directly from my first position to the second, or if I went to the moon and back, it's still 27 joules. Yes, ma'am. Comment?
Yeah. So if it's minus 7 plus 30, wouldn't it be 23?
Oh, you're right. Thank you.
Cool.
Well, no, wait a minute. Sometimes I deliberately do that, folks, to see if anybody's paying attention.
I'm going to need some extra credit on that test.
Oh, you bet. This is John, isn't it? I know your voice. Pardon? All right, now that I hear you together, I got you. Thank you, Justin. You may want to include in your homework. Remember, Ms. Dewberry, the 27 joules, which became 23 when we were paying attention? I do that. How many of you noticed that the very first PowerPoint that had velocity graphs and acceleration, does anybody remember what I deliberately did in that presentation? I had the wrong units for the y-axis. Go back and look at that. Nobody caught me. Ladies and gentlemen, when you're drawing graphs and homework, if you don't label the axes, you get points counted off. I don't know if any of you know that. That's how you're missing points. Labeling, telling me, communicating with. Thank you very much, Justin. John's got some points already. He's just trying to share them with you.
No problem.
I only got 3 pages to go. Work then, and here's a summary of all of this. Notice that consider the first term, it's a projection. The words that I was using in order to develop this, and I did correct it, Justin, to let the students know before you actually saw the finale of the thing that I can add and subtract. I have a little levity sometimes in my work. Here's something that you've done in 2 or 3 homework problems. Additionally, find the angle between the applied force and displacement. Remember, the dot product, F dot R, and notice that I'm just looking at a resultant value here, or it could be a change in R, times the cosine. And I move the cosine out from the force and R, kind of isolated. And obviously, I am using the correct answer here. I go ahead and put the values I got for the dot product, and then I determine the magnitude of the forces. The magnitude of force is the square root of the f sub x squared plus f sub y squared plus f sub z squared, and a lot of you don't show me that particular step in your homework. Be careful. I've had 2 examples of people that put the wrong values in because they did not have the second part of the solution to problems, and that is where you substitute your data in the variables. I found that, and then, of course, for delta R, if you go back and you'll find that r sub x squared plus r sub y squared plus r sub z squared, taking the square root, you'll get 6.16. Substitute that into the value of the dot product and what it means, knowing either f dot r or knowing f, the change in r, and the cosine of the angle already between them, you can solve for the angle between these vectors. This is the only vector multiplication that you can determine the angle from. If you need to determine the angle between 2 vectors, you must go to the dot product. Notice it will extend through all 3 unit vectors. Okay, the last, I hope I didn't go too fast. I think I went slow enough. The book also has a similar example. I have a representation of a force that's coming out at you, and notice, I hope it appears to be spearing out at you, and an R value, and what it looks like, hopefully in 3 dimensions. I wouldn't guarantee. Sometimes people will stand up and they have their arm going, and the center of their torso would be the reference. One arm being in the direction of the force based on some kind of X, Y, Z axis in the room, and R going in the other position, and they can spatially see the angular orientation. Ladies and gentlemen, when I was at Florida and they were talking about solid state vectors or solid vectors, 3-dimensional vector algebra, while we were taking the class, the professor said, I don't want anybody's arms above the table when you're trying to find out what the angle will be. In fact, he said, I prefer that you use pencils to try to figure out exactly whether or not it's an obtuse angle or an acute angle. So there is a little trick here. If you use 2 pencils and try to put them in some kind of spatial orientation, you can figure out if it's going to be acute or obtuse. And that was a great big shortcut or secret. Okay. I just want to go a little bit into our next lesson, but I'm going to start this lesson. I'm not going to go to all the simple stuff, but I'm going to start with this lesson next time. And it says force and displacement graphs. I do not have enough time to go through it, nor did I intend to, but I'd like to get you started on graphic analysis. A lot of engineering is to have a technician develop a graph of some kind so that the qualified licensed engineers could interpret what was happening and does it make sense. And notice a lot of inertia is embedded in this truck carrying off, looks like soil for somebody's whatever. And I really want to concentrate on the work done against the inertia of an object. And the inertia of an object is its mass. It's its unwillingness to change its state of motion. Oh, there's Newton's first law. I have less inertia than an elephant. At least I hope I do. And it's easy to push me over. It's very hard to push an elephant over. First of all, its center of mass is probably taller than any normal height person. What I start with, and this is about where I want to be, consider the given graphs, which contain three distinct force intervals that are not related to one another. Interval A, B, and C. C is meant to be a parabolic shape. They did not have shapes as such when I did PowerPoint, so I did the best I could with connecting dot to dot and then make a straight line out of a curve. I have intervals of position now, not time. You can then tell by the force in newtons and the position in meters I'm dealing with something that's going to give me work. The first interval is a constant force that displaces something from x1 and x2. This second interval between x2 and x3 with a reference point that crosses the x-axis so that the force at this instant is 0. Whoops! This implies that force at the start plus force sub 4 is decreasing to a value of minus force sub 4. What can we conclude from this second interval, which is in dark blue? I can conclude that the acceleration was not constant. Newton's laws cannot be applicable. Uh-oh, we're in trouble. And certainly, if the slope of that line between intervals x2 and x3 is not 0, then the parabolic shape here is not 0. There are two ways to analyze graphs in physics. You can either use a slope, which is the derivative of the function, and some of you messed that up on a problem on the last test. You need to go back and see if you did it. Or area under the curve, which is integral of the bounded function. Please review those words. The interesting thing about physics is since the functions must be polynomial, polynomial functions are functions of real life. They have no negative exponents. Polynomials in physics must always have at least one real root, or it's not a real situation. You're not going to get into imaginary distances. It should be evident that work done during an interval between A, B, and C would be the area under the curve. Unit analysis helps here. Area under this curve would be a Newton times a meter, or the length times the width. And notice in the middle interval, there's as much positive work than is done negative. So the net amount of work going from x sub 2 to x sub 3 is 0. And this is typical of simple harmonic motion or the oscillation of an ideal spring. Now here's where I'd like to kind of talk to you about chapter 15, sections 1 through 10. In the PowerPoint to chapter 15 is an older version of their PowerPoint. I am only interested at this time in you reading sections, PowerPoint frames 1 through 10. However, your general physics course should have introduced you to the equations that are unique to springs or simple harmonic motion. With that in mind, let me go one more frame here. Notice that I have an area under the curve. It is a rectangle, so it's force times the change in x, and then you can just call it whatever the value is. You don't have to say area under the curve. You might say using the area under the curve in your homework. Notice the force was constant, and also the displacement. Oh, let's just go one step further. In region B, and it starts talking about variable force of a spring. Actually, it's an ideal spring, initially compressed a distance x sub O, and then it's either been compressed to go back to x sub 2, or it has been elongated to go to position x3. The first half compression is positive work, area above the x-axis. The second half elongation is negative work, area under the x-axis. And each half cycle or multiple thereof, a whole cycle, a cycle and a half, an ideal springs oscillation in an ideal springs oscillation, the net amount of work is 0. It is a conserved system. So we're looking at some facts here that we will begin to study in the future. This is the frame that I would like to stop with, because with the assumption that you may not have discussed ideal springs in your general physics, I have added a little lesson here in a compressed and elongated spring. If, in looking at the PowerPoint to Chapter 15, frames 1 through 10, it will give you a little more meaning of what is happening here. But I am not going to be taking to concepts in Chapter 15. I'm going to be using them as they are used in Chapters 7 and 8, and I'll be reminding you of that. I have only one problem from Chapter 15 assigned in order to link the two chapters. At this time, I would like to remind you that as you leave the conference early today, you are to get out of Canvas, go to your FSCJ email, and do a trial transmission out of Canvas, preferably taking a photograph or handwriting the following: I want my 10 homework points. Or, if you want to be polite, say, please, I have my 10 homework points. Or if you're in a hurry, just say 10 HW question mark. Anything that relates to 10 homework points. And I will be looking at that almost immediately, probably certainly by midnight, because we want to know how it becomes an email to me. And if we can avoid every one of those not going to clutter, we would have succeeded in trying to solve a problem, ladies and gentlemen. So I'm going to go back to conference. Get out of here. Yep. Okay. Web. Oops, got to enter it. And I'll be able to see some of the comments that some of you have made while I was, okay, yes. Y'all didn't miss much. Okay, sounds good. You are dismissed. And so if you begin to go out of conference, I will try to get this page on procedure fed to Canvas if they allow me. If not, I'm even thinking about maybe mailing you a copy. I do not have the virus. I'm being very careful at my age not to get it. But if I do send it to you, they tell me the mail is probably okay, but I'm not going to be insulted if you Lysol the whole thing. That's meant to be a little bit of a joke, but it apparently works. So I'll say good evening, dear. Pardon?
Quick question. The assessing to learning thing, do we just submit that with the homework or something?
Yes, you may. You may want to say PowerPoint, excuse me, PowerPoint. It's best if, I don't really expect you to write the question, but please identify the variables by listing them, and I'll know which of the 10 you're working on. If you wanted to label them 1 through 10, that'd be fine, and just say, I'm going to skip this one. But numbering can get you in trouble because it may not be the one that you're on. I'm going to recognize the variables that you use. Remember, one was like all ones, less than one, greater than one. One was in threes. I know these selections, so that will clue me in. Okay.
Okay. Thanks.
Yes. And it is optional. You are not required to answer those questions because they go more into what is happening between the moon and the earth and stuff like that. Expands it a little bit. Although I've never had a student say they want to be an astronomer. In my entire teaching career, I don't know that I've ever had a student that became an astronomer. They're all engineers making a lot of money. Okay. Good evening, everybody. Don't forget to get out of Canvas, please. Thank you.